morning, everybody. The outline for today's class is first, introduction to work. Within this topic, we're gonna see things like analogy with mechanical work, where you're gonna try to trace a parallel between the mechanical work that you know from college physics and the thermodynamic work that you're gonna study today. Then we're gonna define the units that are commonly used for work in thermodynamics. Second, we're going to start the study of thermodynamic work by itself. And then, one important thing about that is to study compression and expansion work in ideal gases. We're going to see very in-depth how it works. An important part from compression and expansion work in ideal gas is the sign convention. It's really important because it's going to impact later on when studying the first law of thermodynamics. So we're going to see how to keep consistent the signal when you're working with work, okay? And third, then we're going to study how the work can be used and apply in relation to the calculation to some thermodynamic changes in ideal gas. Okay, let's begin our study about work. And as we told before, we're going to try to trace some analogy with mechanical work. So let's suppose there is a volleyball sitting on the top of the table, like the picture that you're seeing shows us. So the volleyball is the top of the table. The table has a certain height in relation to the floor, a certain height that you call 8i, 8 initial in this case. And to try to make things simple, let's consider that the ball is a point mass having a mass m and is subject to acceleration of the gravity. Then, as the ball is subject to acceleration of gravity, so there is a gravitational potential energy, as we call by the acronym GPE, that's related to the ball by the fact that is in the top of the table in a certain height in relation to what we call like the reference point 0. That's the ground in this case, okay? And the gravitational potential energy that ball has in this position is the product of the mass of the ball, the gravity acceleration, and the height from the top of the table until the floor. Then, we suppose that the volleyball falls from the tabletop to the floor, like the picture is showing us right now. Then, now the ball has the center of mass of the ball has a certain height in relation to the floor that we call 8F. And now the gravitational potential energy of the ball in this second moment after it has fallen from the tabletop to the ground is again the product of the mass ball. It's the same gravity acceleration g, but the height changes is 8F. Trying to introduce the idea of work to our analysis that we have done so far about the gravitational potential energy, we can say that the work made on the volleyball will be equal to the variation in the gravitational potential energy, as it's shown in the formula work is equal to delta GPE. So if we expand the formula, we can say that work is equal to the difference between the final gravitational potential energy and initial gravitational potential energy. The final gravitational potential energy, GPEF, is the one after the ball has fallen from the tabletop. And the initial GPE is the gravitational potential energy before the ball has fallen from the tabletop, when the ball was sitting on the tabletop. Then if you input in this formula each of the individual gravitational potential energy, we arrive in the formula that work is equal to the product of the mass of the volleyball times gravitational acceleration times the difference between the final and the initial height. That's what we call equation 1 at this point. Then we can recognize in equation 1 some things that are familiar to college physics. We know from college physics that the Newton's second law tells us that the product of mass times gravitational acceleration is equal to force. So yeah, the product between the mass and gravitational acceleration is equal to gravitational force, Fg, as we show here. Then we can you can write the equation 1 by introduce the force concept on that, and you arrive that the work is equal to the product between the gravitational force, which was the force responsible for making the ball fall from the tabletop to the floor, times the difference in height. Then, in a more general and compact way, we have equation 2 that says exactly what I had told before. Work is equal to the product of gravitational force times the difference in height, delta H. At this point, we have two different equations, and each of them they give a slightly different definition for the term work, at least for mechanical work that we have done so far. According to the equation 1, we can define work as the variation in gravitational potential energy between the final and the initial moment. And on the other hand, equation 2 define for us that work is the product between a force and a distance, okay? And keeping in mind that force and distance are components of the work, the product of these two quantities is going to help us ahead to understand the units related to the work. Just to summarize and put things in more formal terms, if you look closely to the equation 1, we see that there is a product between mass, gravitational acceleration, and delta height or delta distance, final height minus the initial height. If you can say that in a more formal way, we can state that work is the variation of potential energy between final and initial states. Now, looking closely to equation 2, we see that work is the product between a force and a delta distance or delta height. And if you want to state that in a formal way, we can say that work is the product between the force acting on the system and the distance traveled by the system due to the action of that certain force. After we have already defined two possible definitions for work, now we are comfortable to start talking about the units. And again, we're going to take a look on the equation number 2 that shows us that work is the product between a force and a distance, as it was told before. So we know that International System says that force is measured in Newton, whereas the distance also according to SI, International Units of Systems, distance is measured in meters. So the product of these two quantities, force, distance, and its units, respective units, Newton times meter, produce a unit that's called joule. A joule is the official unit according to International System, SI of units for work. So work is measured in joules. Up to this point, we have studied some meanings of the work related to the mechanical work, and we are able to define that the work according to the International System of Units is measured in joules. Now we are all set to start studying thermodynamic work, and a special case of thermodynamic work is what's called expansion or compression work in the ideal gases. The system that we are going to study again in this case is a ideal gas which is enclosed in a cylinder where there's a piston on the top, and this piston can move upwards and downwards very freely, waveless. And we start our study looking again in the equation 2. That's defined that work is the product of the force times a delta distance or a delta height. The case for the ideal gas, we can express this force. It's not like exactly a gravitational force, but we can express this force being more general by the product between pressure and area. So force equals pressure and area, okay? Then, if you input that formula that force is equal to pressure times area in the equation 2, we arrive that work is equal to pressure times area times delta H or delta distance. And what is worth to observe is that the product of the area times delta distance or delta height is actually equal to delta volume, a variation in volume. So we arrive in a new equation that we'll call equation 3, that says that the work carried out by a gas or ideal gas or unideal gas, which can be expansion or compression work, is equal to the product of the pressure times the delta volume. And this equation can be written in the differential formula. So the delta work is equal pressure times the delta volume, okay? Or differential work is equal pressure times differential volume. On this point, it's very important to clearly define what this pressure is, okay? So by definition, this pressure is the external pressure because the force that has been that has been acting on the system is an external force, okay? So this pressure would be an external pressure. However, we can approximate that in equilibrium, this external pressure is equal to the gas pressure, okay, as things are happening in equilibrium. Between the expansion and compression work in the ideal gas, the first case that you'll be studying is the compression work, and also its sign convention. So we have the gas in its initial state, then some force is applied in the piston in such a way that the gas volume is reduced, so the gas is compressed. We can see the difference between the initial state where the molecules were distributed more apart from each other, and then some force is applied, the piston goes down, and the ideal gas molecules, they become closer to each other. There was a volume reduction, there was a compression of that gas, okay? It happens because the surroundings, they made some work on the system which pushed the piston down. And to do the math related with that compression work, the starting point is the equation number 4, when you have differential work equals pressure times differential volume. One meaningful difference between this time where equation 4 has been presented and the time it was presented before is the negative sign in the front of pressure. And this negative sign appears because the force and the piston displacement, they are done in opposite direction. So the force with pressure times area, it acts upwards, but the piston is displaced downwards, which takes that negative sign to appear in the equation 4. So we have the final state where the gas was compressed, so the volume was reduced, and if you look back to equation number 4, we have The differential work equals minus pressure times the differential volume, and as the gas was compressed, so the final volume is smaller than the initial volume, which leads us to see that the differential volume is negative in this case. Consequently, if you input a negative differential V on equation 4, as consequence, you are going to obtain a positive differential work. Okay? In this sense, we can summarize the compression work by the following statement. So, when the surroundings make work on a closed ideal gas system, the gas volume is compressed, which results in a positive work. Now, we are going to study the other case, which is the expansion work and its sign convention. So we had the same initial state as before, but in this case, the piston is going to move upwards, and the gas volume, or the volume occupied by the gas, will be uh, larger than it was in the initial state. It happens in this case because the gas with the system made work in the surroundings, which pull up the piston. Equation number 4, as you already know, in this case, although the force and piston displacement are both upwards in the same direction, we need to keep the negative sign in the equation for sake of consistency. Imagine if you had like change, it would make like things messy, it would be hard to distinguish, and there will not have like a common ground. So by definition, we always use initially the equation 4 with the negative sign, okay? We have the system in its final state where the piston was moved upwards and the volume occupied by the gas is larger than the initial volume, the volume in the initial state. And looking one more time to the equation 4, as the gas suffered expansion, we have that the final volume is larger than the initial volume. Consequently, the differential volume would be positive. And if we plug a positive value for differential volume in the equation 4, we are going to get a differential work that will be negative. In this sense, we can summarize the expansion work in the following way. When the closed ideal gas system makes work on the surroundings, the gas volume is expanded, which results in a negative work. Summarizing what we have studied so far about the sign convention for compression and expansion work. For compression work, it's the surroundings which make the work on the system. Then, as a result of that, the gas volume is reduced, which takes to a differential V negative. Consequently, looking back to the equation 4, as the differential volume is negative, the work will be positive. For expansion work, now that's the system which makes work on the surroundings. The gas volume increases, which takes to a differential V positive. And if we plug a positive differential V on equation 4, we're going to get a negative work. So what equation 4 calculates is not the work itself, but it's a variation of the work. It measures how the work varies with the variation of the volume, okay? So in order to calculate the work itself, we need to take the equation 4 and integrate that equation in function of the volume, as we're showing here. So the work would be equal to minus the integral of pressure in relation to the volume variation. And to be able to perform that integration, we are going to need some mathematical expression that gives pressure in function of the volume. And for ideal gas, we have that expression, which is the equation for the ideal gas. That's pressure times volume equal to number of moles times the gas constant times temperature. We take the ideal gas equation and find a way to isolate the pressure on that equation. We're gonna have that the pressure is equal the product between number of moles, gas constant, and temperature, all of that divided by the volume. Then we have that the work is equal minus the integration of pressure in function of volume. So we plug that expression that you obtain after having isolated the pressure from the ideal gas law, and you get what we call the equation number 5 from today's class. So equation number 5, today's class, gave a very general expression about how to calculate the work for the ideal gas. It says that the work is equal minus the definite integral in function of the volume from the initial volume until the final volume of the following expression: number of moles times gas constant times temperature divided by the volume. So as I told before, it's a very general expression, and then we're going to see later how it can be tuned for the case of isovolumetric, isothermal, and isobaric change of states. Some conclusions about the equation number 5. The first of them is that as the equation number 5, it describes the variation is in relation to the volume. So for isovolumetric changes, the result of the work always will be 0. It's not possible to do the work in the system or the system do the work in the surroundings in an isovolumetric change of state. So for any isovolumetric change of state, it's possible to say 100% sure that the work would be equal 0. Now let's see the case of isothermal changes, okay? So if you look again to the equation 5, if the change is isothermal, we need to treat the temperature as constant, okay? So by considering the temperature as constant, we get the following expression, okay? So we have that number of moles, gas constant, and temperature, they become all constant. They don't depend on volume at all. So they are leave out the integration. And then we have the following integration, definite integration, 1 over V in relation to variation of the volume, okay? 1 over volume in relation to the variation of the volume. And this integration is very well known in any calculus book, so you can consult the calculus book that you wish, the one that you prefer. For sure that will be present in all of them. So this type of integral can be described that as the integral of 1 over x in relation to delta x, and the result of this integral is natural log of the final x over the initial x, okay? Then if you apply this integral to what you have in relation to volume, like just simply replacing x by v, you're gonna get that the work made in a by ideal gas or on the ideal gas in an isothermal change of state will be the equation 6, that for isothermal change of state, the work is equal to minus number of moles times gas constant times temperature times the natural log of final volume over initial volume. Finally, we are going to study the isobaric change of states and how to calculate work on those cases. So we have the expression for the work. We know that the work is the minus the definite integral of the pressure in relation to the volume variation. And we're going to see that's much simpler than the isothermal changes, for instance. So if the pressure is constant, we treat that as a constant. By that, I mean that the pressure comes out of the integral part of the equation. So we are left with simply with the integral of definite integral of 1 times the volume, the differential of the volume, the integral of 1 in relation to the volume. So it's pretty simple. We end up having that how to solve this integral is simply the difference between the final volume and the initial volume. That's what the equation 7, how we can calculate the work for isobaric change in an ideal gas. It's simply minus the pressure, as pressure does not change, so it's the same in the initial and the final state, times the final volume minus the initial volume. Thank you so much for watching the class today. That's all that I have. I hope you have enjoyed and learned a lot. And please don't forget to like and subscribe to our channel. Your presence, your view, and your interest are really appreciated by us. Thank you so much. See you next class. Bye.